us move on now and just summarize the discrete time Fourier transform that we have learnt. Very quickly you have the synthesis and analysis equations, and it tells you what under what conditions the discrete time Fourier transform exists, and also tells you what is the energy decomposition equivalent corresponding to the signal decomposition. You should not forget this. In this world of transforms, we are not only looking at signal decomposition, but also energy or power decomposition, as the case may be. So, let me summarize now the confusion that you have had until now. This is a systematic arrangement of the confusion, hopefully it clarifies certain things. Continuous time signals, right, have aperiodic spectra. When I say continuous time signals here, continuous time signals which are aperiodic also. What about periodic? Is that also true? Both, right? So, I do not have to specify periodic or aperiodic. The moment I am looking at continuous time signals, the spectrum never repeats. That is because of the nature of the sinusoids, which make up the family of building blocks. Discrete time signals, regardless of whether they are periodic or aperiodic, they have periodic spectra, whether it is energy spectra or power spectrum, they are periodic. Periodic signals, regardless of whether they are continuous or discrete, have always line spectra, that we have seen, whether it is a continuous time periodic signal or discrete time periodic signal, you always have line spectrum. Why? Because only fundamentals plus harmonics can participate, others do not have any role in the family. Aperiodic finite energy signals have continuous energy spectra. So, do you notice a duality there, right? The line spectra can be thought of as discrete, you can say. So, when the time axis is continuous, spectrum is not periodic. When the time axis is discrete, then spectrum is periodic, correct? When in time signals are periodic, again it is a dual, you can see that the spectrum is discrete, and when in time the signal is aperiodic, the spectrum is continuous. Okay. Now, of course, always continuous spectra, whether you are looking at discrete time or continuous time signals, as long as the spectrum is continuous, we can think of a spectral density, which is what we have done. Now, regardless of whether a spectral density can be defined or not, we can always think of a spectral distribution, which tells me how much energy or power is contained in a certain frequency band. If you are confused, you can actually now draw upon the analogy of probability density functions. When the random variable is discrete valued, what happens? Do you have a density function? No. You only have a mass function, which is a line, right? F of x, if you the small f of x, if you were to draw, it would look like a line, similar to line spectrum. That is the case of your periodic signals. Whereas, when the random variable is continuous valued, we can afford to think of a probability density function, correct. But in both cases, I can always think of a probability distribution function, which we call as a cumulative distribution function. So, same story here, whether we can think of a spectral density or not, we can always think of a spectral distribution function, and a spectral distribution function is defined in the same way as the probability distribution function. If you look at the expression that I have given, it is the cumulative one. Of course, I have only given this for discrete time signals, because we are only going to work with discrete time signals by and large. Therefore, the limits of integration on the right hand side expression in the equation there, the bottom limit begins from minus half, the lower limit, and goes up to f. If you recall, we had similar expression for CDF, which is probability of x taking on less than or equal to x, but here we assume that the left extreme is taken care of. The left extreme in the case of discrete time signals for frequencies, the left extreme is minus half. Okay. Or you can say that the spectral density is the derivative of the spectral distribution, but you can say that only for continuous for aperiodic signals. For periodic signals, how does the spectral distribution function look like? Sorry, how did the probability, how did the CDF, how does it look like for discrete valued random variables? Step like. Same story for the spectral distribution of periodic signals as well, right. For periodic signals, there is no frequency component between two frequencies. It is either fundamental and then or harmonics. So, when you add up, you would get a step like shape. So, story is the same, fortunately, so that it becomes easy to remember. So, this kind of summarizes the theoretical Fourier transforms that we wanted to study, which has given us a lot of insights into how signals can be analyzed, systems can be described and so on. But now we have to worry about practicality. How do I apply these transforms when I am given some time series or when I am given a bunch of observations, even for a deterministic signal, right. I am just given some n observations. How do I apply? None of the definitions that we have learnt allow me to apply in a straightforward way. For example, the most practical one that I can think of is discrete-time Fourier transform. Why is it so practical? Because it assumes that signal is discrete in time, that means you are dealing with sampled signal. Moreover, it assumes that the signal is aperiodic, which may be the case. Even there, what is the problem? What is the definition of your DTFT? It says sigma, the expression is xk times e to the minus j 2 pi fk, k running from minus infinity to infinity. This is your x of f, right. This is the DTFT. What are the issues with using this in practice? The first obvious one is that it assumes the signal is infinitely long and I have a full history and future everything, which I do not have in practice. So, that is the first limitation. Okay, let me say I give you that. I tell you that the signal is 0, like our pulse that we saw. Signal is non-zero only over a finite time and 0 otherwise. Let us say that is the signal that I give you. Is there any further problem in using this expression? So, let us say that the signal exists only over some interval, right, some k equals k1 to k2, no problem. Even for such signals, I say there is still an issue with this expression. What would be that expression? I mean, what would be, sorry, that issue? Can you quickly think of what issue we may have here? No convergence, it is finite duration as long as it is bounded. It is nice, it is a finite length signal, no convergence issue at all. Let us say you want to code this, you have to compute x of f, let us say you have to do this in R. What is the first thing that you will have to do? I give you xk from k1 to k2, I give you the values. Finite length, no problem. Something very obvious, maybe you are not actually stating it. If it's sometimes if it's too obvious, it becomes difficult to state. You cannot compute x of f at every point, right? What is the interval for f? Minus half to half. Can you give me x of f at every point? We cannot, right? It is like computing the value of a function at every point in a continuum. What do? We choose to compute over a grid or we sample. That is exactly what we need to do here. We need to sample now. Until now we have dealt with sampled signals in time, but now we have to sample signals in frequency domain. In other words, put in very practical terms, I can only compute DTFT for finite length and over a grid. right. Now, I do not know what should be the grid spacing. These are the questions that we will talk about tomorrow, but before we do that we will just quickly go through the properties of DTFT. They are fairly straightforward. Once we do that, tomorrow when we come to the class we will talk of DFT, the discrete Fourier transform, where we drop the t also. Until now we have been saying discrete time Fourier transform. Why? Because we are emphasizing the fact that only in time the signal is discrete, but in the frequency domain it is continuous. But now we have decided for practical reasons I have to now discretize frequency as well. Therefore, we drop the t. Now we simply say DFT. It is actually healthy for us. We do not have to actually utter one more sound, right. So, we will look at the DFT, concept of DFT and periodogram, but before we do that we will just quickly parse through some of the useful properties of DTFT, and we shall observe that DFT also preserves most of these properties except with some minor variations. When you use FFT in any software package, what you are actually doing is you are computing DFT. FFT is only an algorithm, it is not, it stands for fast Fourier transform, it is only an algorithm for computing DFT. It is not a new transform yet again, fortunately for us. Okay, it is only an algorithm that was conceived by Cooley and Tukey in mid 60s. Until then computing Fourier transform was a nightmare, okay, because of the number of computations that one has to perform. Today you have really very efficient algorithms for computing FFT. All right. So, we will meet tomorrow and then go through DFT and periodogram. Thank you.